Hey, Jason.
Jason,
We
I've
just
never
started.
seen you with a beard.
Trying to relax a little bit.
What the hell? 3 days of sunshine in Boston.
Well, hello,
That's
everyone.
funny.
A happy Memorial Day. It's the EZKL Community Call, May 29th edition. And we were just talking about the fuzz test implementation that we got done this morning, right, Dante?
Yeah, so the idea, so we discussed this last week, and I know that the Noia team in particular had wanted this before they launched in production. So the idea was to create a fuzz testing pipeline where you could basically fuzz over, like, say, proving key inputs, verified keys, potentially like public inputs, just to make sure that your verifier doesn't accidentally verify like bad proofs or something, or just to make sure that like some adversary can't easily break your proving pipeline. Originally, I was going to use something like what we discussed last week was to use something like Criterion or the Rust fuzz testing pipeline. The issue with that is that we're operating in a very particular setting, and we need to be able to generate like, I guess we need to be able to fuzz over like kind of strange objects. So you need to be able to fuzz over proving keys. You need to be able to fuzz over like the parameters or like SRS strings and all this other stuff. So I just ended up creating like our own fuzz testing pipeline, which fuzzes over those sorts of things, and fuzzes it end to end. So it's going to fuzz over each of those possible inputs, like your proving key, your verifying key, all that sort of stuff. And then, yeah, make sure that nothing breaks. But yeah, this is mainly useful if you're like thinking about launching these things in prod and you want to make sure that, you know, like A, our library does what it says it does, and B, that you haven't accidentally created a model that's like really easy to break, basically. Like, for example, if you have a classifier that, you know, that's targeting some specific target class, you want to make sure that, you know, like a bunch of random inputs isn't going to accidentally land in that target class. Like, for example, if it's like triggering, like, I don't know, if it's saying like you should buy some, or if it's swapping tokens or something, you want to make sure that that's not triggered easily by just random noise on your inputs. So yeah, it's a good way to do that.
Got it. That actually clarified a question that I had. This is more so of the security of the model itself versus the soundness of like Plonk on Halo 2.
It's kind of both. It's also to make sure that the constraints we're generating aren't easily fooled or are sound, basically. So it's both for us, because it's a good way for us to like make sure that these things are sound, but it's also good for when people want to deploy these things in prod, to make sure that like it's also good for other folks to like double check that the things we're making are good. So and also that the model they've created is sound, and it isn't like particularly brittle to random noise. So yeah, that's kind of the idea.
Awesome.
Right, and I think we're gonna want to, yeah, go ahead.
You can continue first.
Well, I was gonna say, I think we're gonna want to deploy more and more tooling like this, which basically just serves as a sanity check. Maybe perhaps like on the model robustness side, where we have like active adversaries or something that are trying to like intentionally break a classifier or something. You can do that with like gradient-less optimization pretty easily, but yeah, that might be in a future PR or something.
Yeah, I was thinking maybe you could refer people to things like clever hunts to kind of generate adversarial examples. Just like fast testing is one way, but then like but then clever hunts does have like a pretty comprehensive suite of tools. Let me just get the repo in like yeah, I think that might be interesting because it's also It's also Python based. So I guess like we could add that into the Python bindings now that it's available.
Yeah, I think it would be super cool, actually. I think we might need to like run it within our own tooling, because I guess if you're running that just on a PyTorch model, you're running it over floating point inputs. And we want to make sure, I guess we'd want to like spit out those statistics for like quantized inputs or quantized weights, just so you have a sense of like how much more brittle your model is after being quantized or something. So that would actually be really cool to wrap into the Python tooling, is to add like adversarial testing into that. I guess
Yeah,
before you even export the model.
cool. I'll make an issue for that.
All right, sweet.
Yeah, it would be really cool for PyEzekiel to just have a command say, hey, I need fuzz testing, and then good to go to make the circuit.
Yeah, I guess, yeah, because I guess there's, and we should probably write some docs on this, like separating the, like sort of distinguishing between the robustness of the model itself versus the robustness of the proving pipeline, which are, they're sort of related, but I think it would be good to just have like some explainer as to like how those things are different. Just to, I guess it would be good to have like an article on like the different points of vulnerability in the proving pipeline, just so people can like know what to double check before they launch in prod and like put these things out. So yeah, because I guess, yeah, if you're coming from the ZK space, you might not be aware of like, you know, the ways in which neural networks may fail. If you're coming from the machine learning space, you may not be familiar with like how ZK proofs may fail and those sorts of things. So like having a primer that sort of unifies all the vulnerabilities across those things might be good, actually.
And do what we can to head off the horrible ZK heists when people are not depending on this stuff and are not aware of all the failure modes. I've explained so many times the fact that you can't trust witness generation, right? Which in some sense is fundamental, right? But it's often a surprise to people when they realize, oh, you can put in any witness you want. The proof system has to be responsible for checking, of course, that that's correct. Because most implementations, including ours and including pretty much every deployed ZK system, of course, generates the witness for you as well as producing proof, usually in the same step, right? But that means you miss this whole class of false or negative tests, right? Negative examples.
Yeah.
I guess what's nice is that we have the sanity check mode, so the safe mode that you can turn on, so you can make sure that like whatever you're generating is also valid at the same time. So we have a switch for that. It just makes things a little bit slower. So as you're running through, it's running all these sanity checks to make sure that the witness is actually what you hope it is. If you're an honest prover, that is, basically.
Jason, I thought that a part of the proof was verification of witness generation, though. Proper witness.
What I'm saying is just that if all you do is use CIRCOM or Halo 2 or EZKL or whatever, and you run a bunch of tests, one of the things you're not testing is what happens if someone patches the witness generation and generates a malicious witness. Because you're generating, so when we run forward pass or when we run a proof, we're running the same commutation as we do in the forward pass, right? But in production, a malicious prover can change the way ZKL works, or change the way CIRCOM works, or change the way SNARK works, or any of the generation functions in order to prove a malicious, to prove something that is not meant to be proved. And if you've missed, and this has been real bugs that have been found in Zcash and other things, if you missed a constraint somewhere, right? Hopefully that won't happen because of the compiler and because of the sanity checks. But if your system has missed a constraint somewhere, like if it's a handwritten circuit, you will never notice, and this is not really it's not really apply to EZKL because it's not a handwritten circuit. But if it's, say, like a CIRCOM circuit that you wrote yourself, and you only test it against your own witness, you'll never notice the fact that you missed a constraint.
Wow. Yeah.
Because you have to do
And part
just
of
one doubt, like,
yeah.
what is the meaning of patching the witness?
So what I mean is that there's sort of, you can think about, there's, say, let's say 3 steps, right, to a system. Step 1 is generating a witness. So what we claim, in our case, the witness is the input and all the activations throughout the circuit. But in general, it's just the value of, like in a CIRCOM, the circuit would be the value of all the signals, the entry, and all the advice columns of Halo 2, right? So generating those values. Then you use those values to produce a proof from them, right? By doing some mood math, whatever, right? And then later on, the verifier checks that the thing that you checked is correct. And in most, what I'm saying is that in most systems, you generate the witness, like, you know, someone has given you code, like code to run a DeFi app or something, right? Or roll up code, whatever, just for the transaction. They use that same code, that same binary, to generate the witness and to produce the proof. But you, as a software author, as a system author, have no control over the witness that will actually be generated at runtime. In other words, it's tricky to do it, but the end user could change the code to produce a witness in a different way that proves something different. And as long as your constraint system is correct, you know, as I expect that it is, then that's not a problem. That the proof won't go through. But if you've made an error somewhere in the constraint system, if you left out a constraint, for example, then it becomes possible to generate a proof that will verify if you do this patching thing. Yeah. And that's what I mean. Like, this is like a somewhat subtle failure mode, and I think it's subtle in the sense that it's often something that that you don't think is possible until you dig into the way that the systems work.
And I guess, yeah, part of the reason we've been trying to reduce like our operator set to like a very small number of operators is because it reduces like the number of operators that can fail or be bad, basically. So like if we have Einstein summation to represent all of our linear operations, we just have to focus on the security of like our Einstein summation constraints instead of like, you know, matrix multiplication plus like convolution plus like something else plus blah, 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 blah. So by having like a single way of representing operations and generating constraints, we basically reduce the surface area for failure or on our part, basically, as we're developing the library. So that, yeah, that's kind of a good way to like think about how we want to take the library going forward, is that we want to reduce like the surface area as much as possible of things that can go wrong. And the less code you have, the less operators you have, all that sort of stuff, generally the more secure you can be.
For fuzzing in this case, is it a completely just random process, or is there some particular strategy around, you know, brute force attacking an ML model?
Yeah, that's what I was saying at the beginning. For now, the pipeline is just completely random. The idea would be to start folding some of these adversarial pipelines into like some of the Python tooling. So before you even export the model, you can like check like how if the quantized model, once you've quantized the weights and the inputs to like integers or something, like how vulnerable is it to adversaries? And this is more relevant to classifiers. Yeah, it's also relevant in the case of regression, but I would assume it's particularly relevant in the case of classifiers.
Mm-hmm. Interesting. Okay. Thank you for that, Dante. Did anybody else have any questions on it? Cool. Jason, you want to talk about the new Python binding capabilities? Maybe some benches?
Oh yeah. So right now, more or less like the Python bindings have feature parity with like the Rust bindings, and also you can like did like the aggregations solidity code. So now there's also like sol code being created for the verifiers. So we can now use like aggregated proofs on solidity itself with like both like the Rust as well as Python tooling. So right now I'm working on like the build script for like the Python bindings to be published, and then soon like I'll work on for like the physical library itself. And once that's done, like you can simply like pip install like EZKL and it should work out of the box. Um, so that's going to be done soon. And some of like the security like consideration, because like, I do know that maybe EZKL is going to be used for I guess like for DeFi use cases. I think like it might be an interesting thing to think in terms of like governance wise, like who's going to call like the release function. So right now, I guess like call contributors could help with that, but I guess like it might be interesting to think or just have a discussion around like how like the code base should be audited and who should call like the release, because like this could be a significant point of like a supply chain effects if let's say like like halfway through somehow another like essentially like faulty codes gets like released on PyPy or like Rust binary and people install it. So I guess like this could be kind of a safeguard to have like a human like look at the code base before releasing things. Um, yeah, but that being said, I think it'd be interesting to think of like maybe are there like decentralized ways of going about this? So I guess like Ethan also did mention like there's not specific to the releases, but also how like the verifiers can be maintained on some kind of Ethereum library using a factory contract. Because I guess like if there's going to be many verifiers being created over time, like there might not be a need to deploy the same verifier over and over again because they're simply view functions. So I guess like it would be interesting to open discussions on like how best to do it. So Ethan did propose like a factory contract, so people can call create to function on the factory and deploy the verifiers through that. But there's a catch. Like, so if people deploy out of like the factory contract, like you wouldn't be able to find those contracts. So I guess like ideas around this would be appreciated. So I'm leaning towards like what Ethan was suggesting because it's the decentralized way. The other option is to maintain a registry somewhere off chain of all the contracts that are deployed, but then you have to then trust that registry. So that leads to some kind of complications.
Is there a way to kind of map all of the differences between various models in the verifier? So like, let's say I have an MNIST with just a couple things that have been changed. Is there a way to kind of say no, or to detect that the verifier will be different for the two different MNIST models, even though they're the same?
I think they should be different. So like the models instantly would be the same, but it would be a different verification system because like the weight should be different then.
But what gets interesting though is like, okay, so let's say for example, the weights are private, but the model architecture remains the same throughout those training steps. You could technically use the same verifier because it's just the public, it's the private inputs that are changing to the proof. But if the model, it's with the constraint that the model architecture remains the same, basically. That could be an interesting way to provide like a proof of training almost, and that you submit proofs that like the same architecture is producing increasingly better results at each time step, and then you get rewarded for improving like performance on some held out test set or something. That could be kind of interesting. So you don't actually have to prove that back propagation happened. You just have to prove that like performance improved on some test set, essentially.
So you just submit your new accuracy along with the proof that you trained correctly.
Yeah, essentially. But keeping the weights private almost. Well, yeah, You would have
But
to keep
it's
the
not
weights private in
necessary
that
that the
case.
accuracy will increase, right? I mean, the accuracy can decrease also, right?
Yes, so this is with the caveat that it improves. But what you could do is basically you cut out all the steps where it gets worse, and then you put in the thing where it gets better. So that's kind of the idea. So let's say there's like at step 1, it has 30% accuracy, and then it drops to 25, and then it drops to 23, and then it shoots up to 60. You just submit the step where it achieves 60% accuracy. And so you don't have to like generate proofs for all the steps where it got worse or something.
So the proof generation will take place only at the last step.
Yeah, you would do inference over the test set, for example, and then show that you achieve accuracy of a certain amount or something. This is very speculative. I'm not, I'm sure there's a bunch of
Because
holes
it will
in this
not prove
idea.
that the training has happened, right?
Yeah, but at the very least, you're showing that you have a new set of weights that achieve better performance, basically. That's all you're proving. And that's kind of all you
That's
need
true.
for training to some extent.
Yeah, that's true.
So that would be kind of interesting because like calculating proofs over like the backwards pass and over gradients is kind of expensive. And maybe this is a way to like short circuit that whole process.
Jason, have you thought of any economic models like a token curated registry for something like this, where rather than like content, you just have model verifiers?
Yeah,
People,
it could be possible, right? So you could have essentially hash like the bytecode. So for example, like there could be like a hash of the bytecode and like the contract addresses. But then the question about for TCR is that someone has to then curate the TCR, right? Because it's curated. So
Yeah.
so there's like kind of like this kind of governance issues that have popped in and out. But like after dealing with DAOs for a while, most DAOs are kind of dysfunctional. So ultimately, it's just a couple of people managing things at the end of the day. Yeah, I think like the best way out for now, I guess like since they're kind of core maintainers, like I guess it could so there are two approaches. One of them is like to create like factory contracts and the TCR approach. So I guess I'll be down to like help maintain either or. Yeah, but I guess like the question then comes is like, what if like let's say eventually core contributors leave like the project, then who takes over? And so like it's usually in this transition periods for libraries that like things either die, get wonky, or get forked. So those are the kind of like potential issues that can come out. So I think like planning for longevity is also like one concern. Yeah, but for now I think either option seems like viable.
I'd love to hear from Owen, Michael, Hadi-Arish, like how would you like to see, to the extent that we're helping at all with problems. So I think the problem is like verifying the verifiers. Like, how do we know? How does your end user know which verifier to use, right? And there's a big spectrum. There's many different ways to design that system. The systems we've been talking about, using routers and indirection, using all kinds of stuff, right? So what kind of system is most interesting to you, and sort of how do you think about that trust? I mean, one of the other big problems, of course, here is replaceability. Like, when there's a merit and you want to do an upgrade to a verifier to get something faster, or there's a bug or whatever, you're going to want to change it. How do you want to do that upgrade? How do you want to control it?
Yeah, I think in most cases, like in the DeFi space, at least, most upgrades are done through DAO anyways. So it is kind of trusting that those core members are doing it properly still. I'm not sure necessarily of any models that you could do where you'd be able to, I guess, self-verify as a user. You would still have to kind of trust that, I guess, the core DAO is doing it properly. But in my mind, like for example, if you had like a auto managed vault where you want to verify that actions took place, you would still have that verifier as like a core to your protocol, and upgrade that if you needed to upgrade it. Do that through a DAO, I guess. But yeah.
And by upgrades, you mean like changes to the model, even though it's the same architecture, right?
Yeah, so I think it would be pretty fluid in my mind. Like that would be really interesting to be able to use the same verifier and kind of update the weights. That would be really cool because you could kind of prove that you're not changing anything drastic. But I think if you wanted to, you could have it as fluid as just having your main contract point to a verifier, and you can update that address and still run through like a completely different verifier if you needed to. But I think those are kind of, I guess, like two different routes that you could take.
Interesting, yeah.
Gotcha. I guess, I mean, if you keep at the very least, what you can do is even if you swap out the model, if there's like, I guess if there's some test set that you've committed to, you can, generate some proof that the new model improves in terms of performance. It gets kind of hard to prove that you've like not trained the model on the test set, but I guess it's better than nothing at that point because you have.
Well, you could do like, you could do just like test runs on chain if you want to do, just without any capital. Do test runs, and then you can say that like, hey, this is more accurate than our current model that we're using. Let's swap over to this one. But
That's true, actually. You could almost do like real-time back testing with the new model, where it's like, okay, from this block to this block, we're taking as input all of this on-chain data, and this model that we're keeping private achieves this sort of performance versus the current model. Here's why we're swapping. At the very least, you prove that because the data is definitely held out in that case, because the data is coming through and being generated each block.
yeah, exactly.
So that could be kind of interesting.
You think Axiom could be used for that?
That'd be interesting. Possibly.
For fetching? That'd be cool.
Like for I guess past actions on chain.
Like getting the data from certain range of blocks.
Yeah, I guess you could. My only concern with like doing past data, I guess, is you could just optimize your model for data that you already had.
Oh yeah.
So like, I feel like it might be more interesting to do it like, it would be more costly for sure. Or you could post your verifier first and like check off chain if it's doing it properly. But like, yeah, you could, I guess, post your verifier first and then see after a little bit of time, be like, yeah, it is, it's acting more accurately.
Yeah. Interesting. That's cool. What about Hattie, Michael, David?
So yeah, we are still working on our strategy. Basically, we are standardizing everything. We are making the updating more regular. So we are in that process, and also we are working on how we can prove the backtesting properly in our website, and how we can like show and how we can give this guarantee to our users that this model is not tampered with. So, and also at the same time, translate the output of a model into an on-chain action, both efficiently and meaningfully. Yeah, that's our challenge right now. And
yeah, I think the model verification kind of pool would make it so that they're a lot more trustable. If you say you're using MNIST and it verifies on one of the big MNIST verifiers, then and you're definitely using it.
Mm-hmm. So
That's interesting. Does anybody
I didn't get your point. So you are saying that like publishing our model and using a famous verifier or an agreed verifier in the community?
Are you? Or yeah. So like, if well, the one that you all have is pretty unique. I'm more so thinking about like very common ones. Like the problem that we're talking about is super common ones that people would be deploying over and over again.
Yeah.
Taking up on chain. So
I guess, yeah, it also becomes interesting for like fine-tuning models, because you start with a large model and then you fine-tune it to your use case. You have your own particular ways, but you keep the same architecture. Yeah, that becomes kind of interesting because everyone can use the same verifier in that case, which is quite cool.
Mm-hmm. Yeah.
So I mean, I guess that segues nicely into the models that you might fine-tune, which include GPT-esque models. Yeah, so I guess I'll talk about this. Yeah, sadly, Bianca, who I was working with to get this through, isn't here to discuss this. So I'll be running through all the stuff we did to get NanoGPT into a SNARK, which is pretty cool. Yeah, it took a lot of work to get it to this point. If you haven't read the HackMD post, basically there were three main things, or I guess like three main innovations it took to like get this over the line. The first was basically to like support as many Onyx operators as possible. So transformers are pretty complicated objects. They do like dot products, they do matrix multiplication, they take transposes. You know, they they have dropout layers, they have all these sorts of things, which make it kind of difficult to implement in a SNARK, because our approach originally when we were designing this library was to go through each operator and then implement like a circuit equivalent of like some tensor operation. So that gets particularly dicey when you're dealing with like really complicated like 4D tensors and you're having to take transposes of stuff because you have to re-implement like shape casting and all this sort of stuff, but you have to do that in circuit land, which gets kind of dicey. One of the libraries that we started using recently is something called Tract, which is designed by the Sonos team. And this library is pretty amazing. It's like a very good way to like take a complicated neural network and then reduce it. So you can have, I think in the Onyx format, you can have up to like, there's like 150 different operators, and Tract reduces and simplifies like whatever, any computational graph to a set of 10 or 15 operators, whatever it is. Which means that we only need to implement circuit analogs for like 10 or 15 operators, which is really cool. And in particular, like all of the complicated linear stuff that I was describing at the beginning, like taking transposes and then, you know, dot products over transposes and then complex n-dimensional matrix multiplication and all this other stuff can be represented using an operation called the Einstein summation, which is just a really succinct way to represent almost any linear operation, which is the product or the summation, or it's, yeah, the product or summation of like lots of different tensors. You can represent like over 100 different operations using that, which is really cool, which meant to like get like the NanoGPT Onyx file into a circuit, we only needed to implement einsum, and that was it. That's kind of all we needed. The second thing we needed to do was we need to make Halo 2 layouts faster. I have a whole description of how we did that. So we had to modify a little bit of how copy constraints are generated inside Halo 2, so we could do it in a multi-threaded way. And yeah, combined, all those sorts of things meant we were able to get this into a SNARK, which is pretty cool. The proving times aren't yet practical, in that it takes like 1,000 seconds just to generate a sample for like a smallish GPT model. which isn't great. But as soon as we published the article, a researcher out of the University of Berkeley started taking our Halo 2 fork and adding GPU bindings into it. So hopefully we'll get results of like proving, proving GPT inside of SNARK using GPUs over the course of the week. And hopefully that brings those numbers down as much as possible. I mean, I didn't set this objective, but he said he was aiming to get proof time below a second. See if that's possible. But if that happens, that would be huge. So yeah, stay posted for some updates on that front. But what is quite cool, so the other innovation that we've had here is that we're able to sort of support almost any model size within a SNARK. I guess a lot of other libraries are constrained by the size of their SRS string, like what factor they're using in the ceremony generation. We have a bunch of clever ways to get around that, so that irrespective of the size of the SRS, you can actually fit almost any model inside that circuit, which means that you can prove these things on a relatively small machine, which is kind of what we've done here. Like we didn't need a cluster to be able to do this. It was just a single machine. So it's like relatively hardware efficient, which is kind of cool. But yeah, I guess the really exciting thing would be once this stuff gets into GPUs, we'll be able to like really accelerate this stuff. But yeah, we'll see where that goes. Hopefully there's an update this week.
I have a question about GPUs. So this is going to be pertinent to the build step if it gets implemented. So is a GPUs like OpenCL based or like CUDA based?
Yeah, so I think it's CUDA based. So I think basically, I think we'd have a feature flag.
Is it just me? I think.
Yeah, he wrote it for me too. I just give him some time.
Yeah, I think I'm gonna turn off my video.
Did anybody get how many seconds he said we get to after the GPU bindings? I actually missed that.
Nope, that was cut off on me.
I thought I heard
Yeah, it was
under
cut
a
off for me.
second, but oh, hey.
All right.
Oh wow.
This is why you don't run big computations at the same time you have a meeting.
Yo, your image is still frozen too.
Yeah, my laptop. My memory just got wrecked. Yeah, so basically what I was saying is that I think we'd have a feature flag basically for conditional compilation of our Halo 2 fork, which would be GPU or not GPU enabled. The library that he's using, I think, is CUDA basically. So sadly, it wouldn't be for Mmax, which would have been cool. But yeah, you can easily find something with CUDA in a data center, basically.
Earlier when you were saying you
for the Jupyter notebook version, I think probably, right?
Yeah.
Yeah. Earlier when you were saying you could get it under a certain amount of seconds, I think you just cut off a little bit there. How? What were you mentioning?
Oh, he was saying. I was saying that he's set as an objective to get proving time below 1 second, because currently we're at like 1,000 seconds which is kind of slow. Obviously, yeah, that's quite slow. But I guess what is it? Yeah, the idea behind the project is that it's sort of a forcing function to make the library as robust as possible to like gigantic computational graphs and to support as many operations as possible. And like working backwards from a model is usually a good way to do that. It forced us to like simplify the library and all these sorts of things. Like it actually reduced our code size, which is kind of nuts. But yeah, it's usually a good forcing function for like getting things done, basically, if you have like a really ginormous model that you're trying to get in.
I'm guessing for the GPU bindings, I haven't really looked into this, but like because there's web GPU, it might be possible to just write for web GPU and have it be portable across systems. Yeah, but I'm gonna like explore like the web GPU stuff because there's like the ROS bindings available and it should be like live. So you could technically write in like web GPU and then have it interface with like the underlying hardware libraries like Vulkan, Meta, so on.
Yeah, that would be really cool. I mean, particularly for the WASM prover and all those sorts of things to help accelerate there. That would be quite nice.
100%. Thanks for sharing, Jason.
I'll get the exact name of the library.
Alex,
that's
is there
being
any
used.
information in the HackMD page regarding
You have
the
great-
parallelization of the copy constraints that you mentioned?
As to how, oh yeah, so it's in there as to how we modified it, and everything's in there. There's a description of it. There's a link to the PR as well. The PR has reviews from the
Thank you.
Halo
Thank
2 team as well, so you can verify that I haven't produced total garbage.
Cool. Thank you.
Yeah, and I guess the final thing to discuss actually is like all the WASM related stuff. So like the WASM proving tutorial and all that sort of things.
Yeah, for sure. I was just looking at the web GPU example, and I'm actually curious to see what it would look like to implement that for WASM, because it took a long time on my machine. I'm not running like an M1 or M2, but it still took some time. How long was proving for you, Dante, on the 1L Relu?
I think typically it takes like 5 or 6 seconds, I think.
Okay, cool. Yeah, that's good. That's good. It took me about a minute.
Wow.
But yes, I can send a link to the WASM tutorial. It's a basic tutorial of building a front end with the WASM bindings. And what we want people to be able to do is to, not have to deploy a verifier contract, but just verify and generate proofs in browser. So what you do have to do is run setup on your own instance of EZKL, which is what we're working on now, to have setup run in browser so that you can have the parameters it takes for proof generation and then verification. But yeah, over time, the WASM capabilities will be expanded because we know that a lot of zkml applications don't necessarily use blockchain. It could just be something that people want in browser. I know Danilo and I were talking about this. He isn't on the call today, but essentially what they want to do for Baby Gaia is do state updates in browser and then prove a different type of model on a blockchain, because sometimes you don't necessarily need that. So it's really cool. And then I also think it'll be good for the Web 2 use cases as well. But if you go through the tutorial, it's just a basic setup of how you can get a front end to upload all of your files, like your circuit parameters, your KZG parameters, input, Onyx file, everything, and then prove and verify models.
I'm kind of curious. Oh, sorry.
No, go ahead.
So you're saying mainly for Web 2 applications. Would it not also be like helpful if you have a public model, you could generate proofs for a validator that's on chain?
Oh yeah, for sure.
Yeah,
so
for sure.
Okay.
That's another really, I was about to say that actually. Another great
Cool.
So basically, if you have a web application, you can just generate the proof and then submit the proof as call data to a contract as well. So you can have like your browser clients just like interacting with these sorts of things. I guess a potentially interesting dynamic for like DeFi or something is like, say you have, I don't know, you have some complicated update rules for some pool of tokens, and that usually costs users a bunch of gas. And those update rules are public and known to everyone. Basically, every time someone interacts with that pool, you can have them run the update function within the browser and then just submit the proof that they ran it correctly as a way to save on gas. So that's
Would that work for a private model as well?
No. Well,
Okay.
I mean, it would work if it was private and committed to and shared with the browser clients. But then you're
Okay.
sort of expecting the browser clients to not collude and like share the model. Sorry,
Yeah,
I guess
that
I
makes
mean
sense.
it's like if privacy matters in that situation, you're sort of banking on the fact that the browser clients don't share the model more widely.
Yeah. Okay.
Yeah, but if you were a like a strategy provider in a DeFi protocol, the model could be proved in your browser. You could have it either from the server if you trust the server, or you could have it in local storage or something. You know, and just run your model. You're responsible for running it. It's a little fragile for that kind of thing. I think it would work.
But yeah, I guess it gets kind of interesting if you're like updating weights quite frequently, and that's like a costly operation. And it could be an interesting way to like, you're basically shifting the cost of computation from, you know, the set of validators on the network to the browser client. And in return, the browser client pays less effectively because there's a fixed gas cost for verification in that call.
I'm thinking of a use case where you would want to, let's say you have a public model. How do we okay, so you have a public model and you only have the verifier on chain. Is there any way you could extract the model from just the verifier? I know it hasn't historically been possible, but is there a way in general?
So we don't have any formal results. Well, you mean, for example, like it's a public model with like a specific set of weights. Is that what you're saying?
Exactly, yeah. How do I extract the weight?
I guess what's kind of interesting about our setup, but we don't have like good formal results for this. But my intuition is that given the way we generate constraints, I think the space of possible models that you could extract from the verifier is very, very large. And I think computationally, it would be very hard to invert the circuit to recover the model. Yeah, it's kind of an interesting one. Partially because, and I think this applies more for like very deep models. But the way we use the way we use lookup tables and those sorts of things might make it very difficult to like invert effectively.
Yeah.
But as to like formally how difficult that is, I don't have the results yet.
Got it. It's interesting.
And I guess we mentioned this sort of in passing in the HackMD piece. But yeah, there's definitely, it would be cool to like explore that further because I think that would be kind of a useful property to have.
If one of the PhD or master students that's working on these things is interested in working on that proof with us, that would be a really good way to do it.
Yeah, that's true. That would be really good.
Would that be like a complexity theory problem?
I'm sure there's multiple angles from which to tackle this. What you often find is that you can just pick a branch of mathematics and then use it as a hammer until you get a result. But as to how elegant it is, yeah, it probably depends on the as to how powerful the branch of mathematics you're using is.
It's very interesting.
Because I'm sure you could explain it from like a functional analysis perspective as well. Like that's also possible. I'm sure you could. I'm sure there's like some connection to category theory. It's definitely, there's always a connection to category theory.
I like to think of it as like any area of math, once it's sufficiently advanced, it has like a Turing completeness where it can be used to model anything else. If you're willing to, do the work.
Yeah, I had I have a saying for this sort of like failure mode in thinking, which is like everything is everything. Because you see so many papers which are like blah is blah. Or
I'm thinking of a theory or a category of like lookups and constraints. If you were to use something like that as a basis to go off, like working backwards from a verifier.
well, I guess you would have to start from like our particular framework.
Yeah.
Like how we generate our constraints as well. Because ultimately what makes our proving framework really fast is that we ended up linearizing effectively all the constraints. So they're at most there's like 2 variables inside a constraint basically. So yeah, so the overall like order of these things is quite low. But that also means that you sort of obfuscate what the actual calculation is as well, because you're not really, it's kind of an interesting one. Because instead of just having like a dot product gate, it's actually just the repeated application of like multiplication and summation gates and those sorts of things. So you're sort of obfuscating what the actual underlying calculation is my intuition.
Especially with well, no, INSUM wouldn't necessarily have to do with that because that's not in the circuit layout, right?
No, it is.
Oh, it is, yeah.
Well, yeah, it would also be hard to extract like the INSUM operator just from the constraints, is my intuition. That becomes like a very difficult combinatorial problem, I think.
Jeez. Very hard.
Yeah, presumably. And I suspect that like reducing everything to a single operator has also made it more difficult in this case. Because everything sort of shares the same set of constraints. Or yeah, they're just applied in a different order effectively to generate the actual circuit.
Wait, how would more operators make it easier? Because you're
I guess each one might have like a specific signature, for example, that like distinguishes it from a like, I don't know. But again, this is all like very hand wavy. I don't want to like put too much emphasis on this. Yeah. I don't want to put too much emphasis on this. Until like until we get like conclusive bounds for
an actual statement of what's protected and what's leaked. I think it's probably will work out, but
this is how we get murdered on Twitter.
Yeah, right. We claim that it's a functional commitment, and it's actually, but they go through the proof system. Basically, they have to like go through the proof system with the Halo 2 proof system really carefully, and what the verifier learns really carefully, and make sure that nothing has, or understand exactly what has been leaked.
Yeah. All right.
And under what assumptions?
Yeah. I'm conscious that we have 5 minutes left. So I just wanted to end with like things that we'll be working on this week. So something that we've had requested from lots of different teams is the ability to have the hash of the public inputs as being the actual public input to the circuit. So if this is particularly useful if you have a big public input and you're using it as call data to the verifier. This is a way to reduce gas costs and not like or basically not to exceed the gas limit. So that'll be really handy. It's also a way to like commit to like say weights and prove that they're not varying, but whilst keeping them private, assuming the hash function is an invertible. To begin with, we're going to be using the Poseidon hashing function just because it's amenable to debate. Well, it's like a lot more. It's a lot cheaper to prove in a zk-SNARK. I guess so that's probably going to be the bulk of the work on my end. I guess there's going to be some developments on the WASM front as well, so we're going to be expanding the functionality there. trying to get it almost, well, I guess we don't necessarily need feature parity with like the Rust stuff, but at least expanding it as much as possible so people aren't restricted there. I know that Ethan, who isn't on the call, is going to be exploring like some of the pre-generated verifier ideas, and JSeem's going to keep bashing out some cool Python, some cool Python functionality.
Like one thing that might be interesting is also another issue I posted was with regards to visualization. So yeah, I think that is something that I think we have been discussing internally. So if you guys have any kind of like visualization ideas that might be useful, like what you guys want to see, I think that's something that could also be done on the Python end. So you can kind of put that in like the Jupyter notebooks, which can be quite useful to see like what's going on under the hood.
Yeah, I was gonna say like something that would be particularly useful for me is because we have the Onyx model and then we shove it through Tract and then it gets reduced to a different operator set. Even just visualizing how the model gets simplified afterwards would be quite nice. Because right now the only way we have to visualize it is a 2D table, which is not as good as a graph. So I think that's where Python, like all the tooling that Python has, would be super, super useful. Already there, that would be quite cool.
Sounds good. Oh, right. So like I think the Python build script should be up. So I'm waiting for like the build action to complete. So I'm not sure whether that works, but I got it from most architecture, including for the Linux, Windows, as well as Mac OS. So yeah, if the build action confirms, I think I can just merge it to main. Yeah, I think like the build actions are just like taking extremely long. So like if any like new feature changes are gonna be introduced, like it's gonna like just rebuild every single thing, and it like takes like hours.
Yeah, fair. I think, I mean, something I need to do as well is like reduce the build time for Rust as well. Because like I feel like some of the dependencies are really bloating the build time, and I either want to make them like conditional or something. So we have an issue for this, and I posted like some of the libraries that are contributing most to the build time. So if anyone out there wants to help simplify the build or reduce build time, that would be super useful. All right, just 6:30.
All I need is welcome. Thank you all for coming. I'm gonna go ahead and stop the recording.
Yeah, thank you, everyone.